Okay, so we're just looking at some applications in complex numbers, and this one is about the geometric representation of adding or subtracting and multiplying and dividing. So again, I don't know whether there's going to be any exam questions on that, but just to show you that you can do geometric representations. So just like we had in vectors, if we have two complex numbers, oh sorry about that. If we've got two complex numbers, z1 and z2, if I add them together, just like in vectors, we can do a nose to tail. So this vector, this complex number could be added there, or that complex number could be added there. But at the end of the day, like that is the same as that, that is the same as that, and you end up at the same spot, which will be adding the real parts and adding the complex parts. So it's just it's very similar to vectors. Again, I don't know whether we'll have questions like this, but I'm just showing you what it can happen. Okay, the next one is multiplication, and there is a full proof on this that we could do, but just to keep it nice and simple, if I have two vectors, z1 and z2, and again I'm using this polar form with angles to the vectors, when you multiply, we're multiplying the lengths of these vectors, and we end up with a new vector which is that long, which will be r1 times r2, and the position of it is actually just adding those two angles together. So if I add those two angles together and I multiply the modulus, I end up with this new vector z1 times z2. Okay, so that's useful when we have harder multiplies later on. And again, similar to division, similar to multiplication, and I won't draw it on a graph, but when you multiply, when you divide, you end up with a new vector length of r1 divided by r2, but instead of adding the arguments, we subtract the arguments. Okay? So that's the representation for division. And again, just to keep on the idea of why we're doing polar form, well, once we've got polar form, it's much easier rather than, obviously when we had them in 2 plus 3i multiplied by 4 minus I, it doesn't take us much to do to expand that out, but we don't have to do any expanding out, because when we're multiplying, that's a 5, that's a 2, so the new length is 10, and then I just add the two numbers together, okay, and then lowest common denominator is going to be 12, and so this will be 2 pi on 12, 3 pi on 12, so it ends up being cis of 5 pi on 12. Okay. Now the only thing you have to worry about is make sure that when you add those arguments, you've got to stay in the range. So you have to stay in that range, and if you go outside that, if this number here goes outside pi, if it goes past pi, then instead of going, so if it goes, say for instance we're here, instead of going forward there, you actually have to go backwards to get to the same to the same spot. So just be careful on that. So with division, we just divide, so we get 5, and then we subtract. Okay, and then, so the answer is 3 minus 2, so it ends up being 5, 6, 5 pi and 12. Okay, so this is much easier to use than actually doing that division complicated formula. The last one I want to show you is a really good application of multiplying. Okay, so I'm just flicking my notes. Okay, so obviously that should be I there, sorry. We could do it, 4 times, and then we could multiply it out, or we could use Pascal's triangle, whatever. But let's just use the mod arg form. Okay, the modulus. Okay, so the modulus will be the square root of 1 squared plus root 3 squared, which is the square root of 1 plus 3, which is the square root of 4. So we've got the modulus being 2. We've got, remember that 1 plus root 3i is going to be in that position there in the first quadrant. So we've got tan theta equals b on a, so root 3 on 1. So tan theta equals root 3. So then we've got that as being pi on 3. And so 1 plus root 3i to the power of 4 will be that number, because this number is now going to be 2 cis pi over 3, and we're just going to multiply it 1, 2, 3, 4, so it's going to be the 2 to the power of 4, and then the angles here will be the same angles here, which we're going to add. So we're going to take pi on 3 and multiply it by 4. So 2 4s are 6, 2 to the 4 is 16. Now, 4 pi on 3 has now gone past that position there, so we can't have that as our final answer. And so the final answer is, if you're 4 pi on 3 that way, then you're 2 pi on 3 backwards, because then you've got 6 pi on 3, which is 2 pi. And so the answer ends up being 16 cis minus 2 pi on 3. Okay, and that's the end of that video. There'll be practice for this on the worksheets.